Okay, just real quick, there's two types of bond types that are extremes. The extreme bond types that we have that we can look at, and when I say extremes, it means there are some bond types that are in between covalent and ionic. So when we look at the definition for ionic or covalent, we're talking about examples that are pure examples where we don't have extremes taking place. Okay? It says when class time is over, counselor would like to see Jacob and Mallory. Okay? When we get done. Okay. Just real quick, these are terms that you guys know. Very efficient at knowing these terms. And so one would be ionic. Okay, and the other one is covalent. There is a mixture of the two that is kind of in between. We do list it as covalent, but we call it polar covalent. So polar covalent is kind of in between. The two. All right? Your electronegativity is kind of tell you what extremes you have. So we're starting out with ionic. This is ionic bond that we're talking about. What will happen with an ionic bond? It is formed when electrons are transferred to make it opposite charged atoms. Okay? Any questions with that? So we have ions. Thus, we got ionic bonding. We have cations and anions. You guys know the difference, right?
Yes.
Cations, what charge?
Positive.
Anions?
Negative.
Okay, good. We won't put that down. You guys know it.
Wait, what was it?
So, again, a ionic bond is formed when electrons are transferred to make opposite charged atoms. That's what's going to take place. We've got two atoms. They determine if they bond is if one's willing to give up an electron and the other one wants to accept it. When we looked at the last chapter, we looked at this thing called electron affinity and ionization energy. If it has a high ionization energy, it will not give up electrons. If it has a low ionization energy, it will give up electrons. Thus, over here, they give up electrons. Over there, they keep their electrons. Okay? We also have this thing called electron affinity. Electron affinity is the willingness to take in an electron and give off energy. Okay? These have low affinities, and they have high affinities over here, except for the noble gases. And certain groups that have half-filled subshells. Okay? So over there, they want them. Over here, they don't get much energy off when they get them, so basically, they're probably not going to accept any electrons. So those two areas will tend to ionic bond because electronegativity is quite different between the two. All right? So we get to covalent. Now, a lot of times this is called pure covalent, but covalent is when we have electrons shared between two nuclei. Okay? So it's an equal share. So covalent is an equal share. That's what we're looking at. Fairly equal share. Okay, so an equal share of electron pair. Now, in between these two, you're going to have a situation where it's going to have some ionic character and it's going to have some covalent character, and we call those polar covalent. So, covalent bond, and this is polar covalent bond. These are all bonds that are happening when two nuclei have unequal share of one electron, or pair of electrons. Okay, so when two nuclei have an unequal share of an electron pair, they're still sharing, and that's really a covalent sharing, but it's an unequal share. So that puts it in between ionic and covalent bond. Okay? If you want to look at a chart that kind of summarizes this relationship, page 357, at the bottom, table 8.1 kind of shows you where you have strong ionic character and where you have strong covalent character. Okay, any questions with that? And now we're going to have to decide, what kind of bond occurs using electronegativity. Okay. When we studied this in the past, they gave us two separation points. They said if it's between 0 and 0.3, it's considered covalent. We can consider it's a equal share. Okay, I'm not going to say that to you guys, but I'm going to say if it's a low difference in electronegativity. So right here, if we would put in here what categorizes covalent bond, it would be a small difference in electronegativities. And I'm not going to spell out electronegativity, you guys. Maybe I will. You can do a shorthand. Electro, neg, or however you want to do it. So that's a small difference. Okay? Ionic would be large differences in electronegativity. So I'll say large differences in electronegativity. And maybe I didn't give you guys enough room, but you can write it out the side. I'm running out of room. And then I'm not going to put anything for polar covalent because it's in between. Okay? Polar covalent would be in between. Any questions on that? So let's just take a look at some examples of how you would write and see something that is ionic, polar covalent, non-polar covalent. We'll just list them in order. So we'll just give you an example where we're kind of going to list them in some sort of order. Okay? So let's just do that. So I'm going to give you 3 combinations of a bond, and then you're going to list them in order from most covalent to most ionic. So okay, so here they are. CaCl, P with oxygen, and we'll do C with chlorine. Right? So look at their electronegativities, find the difference, and then list them in order of most covalent to least covalent. Okay? So any questions on figuring out the order? Now, sometimes they'll do something, they'll say, you need to predict. So sometimes they'll go, all right, let's predict if it's ionic, or put it in some sort of order. And so electronegativities get bigger going across, and they get smaller going down. And so what you'll do is you have a combination of atoms together, and then knowing the knowledge of trends, you should be able to predict which one's going to be higher ionic character versus lower. Okay? So if the extremes are like barium with fluorine, that's going to be highly ionic, because these are really low electronegativities and they're really high. And if they're right next to each other, like N and O, then they're going to be similar electronegativities, which means there's not much difference, and so that's going to be more covalent character. Okay? That you do. So that's why we did those trends, so you don't have to look. They'll ask you to predict, and that's kind of why we know the trends. We can do some predicting without looking at the overall numbers. Okay? So we're going to look at this PO, for example, and we know it's polar. So this is going to be polar covalent, because there is a difference between them. Not a huge difference, like above 2, kind of in between. And what we're going to do is we're going to use a delta sign. Okay? The delta sign will indicate if it's... what delta means, basically, is it has a fractional charge. When they say delta, they say a fractional charge. So P is 2.1, and oxygen is 3.5. So which of those have a bigger share of that electron? Oxygen or phosphorus? Oxygen has a bigger share, it's got a bigger number, so the electron's closer to oxygen than it is to phosphorus. It spends most of its time, or the pair does, closer to oxygen. So what we'll do is we'll have fractional charges. They're not pure charges, but they're a fractional charge. And what we do is we use a delta sign. So we can go delta, kind of like an S, and we'll go positive for the lower number. Okay? And then we'll do delta negative. And that shows it's polar. Any questions with that? So anytime you see a delta positive, it means that fractional charge is positive on that side. And then for the oxygen, it's negative. Any questions with that? Let's have you do just a couple, just real quick.
The smaller number will be the positive.
Smaller one has less of the electrons, and so it's going to have a fractional charge as positive. And the one that's higher is going to have a fractional charge that is negative. So we'll have you do a couple of these real quick. So just use that delta sign. So we've done ionic, covalent. Ionic and covalent, you would not use the positive and negative. If it's polar covalent, which is in between, we're going to use the delta positive and delta negative. So on this one, the delta negative would be on the nitrogen, right?
Yep.
And then on the carbon would be positive.
Correct.
Bromine and carbon. Bromine, would it be negative or positive?
Negative.
Okay. Bromine's 2.8. Carbon is 2.5. This would be kind of one of those, we can go ahead and write it, but there's probably not, it's not much of a difference in electronegativity, so It's kind of on the borderline, but if I ask you to do it, what you do is put bromine as a negative, and the carbon is the positive. And then on this one, chlorine would be the negative, and hydrogen would be the positive. Any questions? Okay. Couple more things, and then I'll be done. What we want to do is take a look at what we call polar molecule. So I'm going to show you a couple of molecules, and I'm going to have you do this same thing with these molecules. Okay? And we'll talk about these two molecules. We'll just briefly get into the molecules, but I'm going to give you water is one. Go ahead and do your sigma positive and delta positive, delta negative for that one. And then I'll give you another one here. Don't worry about the double bonds. Okay, that's not going to have anything to do with the positive and negative. So do those two. Water and carbon dioxide. Do those two. And just show negative and positive between the two bond types. Any questions on water? Okay, so this is considered a polar molecule, or it's called a dipole. We have a dipole. It just means you have two parts of a molecule that are opposite of one another in charge. Okay, so we have what's called a polar molecule, and it has a dipole. And a dipole is just difference in charge and separated by a short distance. Is what a dipole would be. So down here, I'm going to circle this area. This area is what charge? Positive. I'm going to circle this area of the molecule. What charge is that part? Negative. So we have a polar molecule. The top is negative, the bottom's positive. Okay? That's all you need to know for now. So now we're going to do this one. This is going to be sigma negative, sigma positive, or I keep on saying sigma, it's delta, delta negative. Okay? This is a non-polar. Let me explain why. There's no net difference on either side of the molecule. Meaning that either side of the molecule is the same charge. Gotcha. And if there's no difference in the extremes on the sides of the molecule, then they cancel each other out. So this is negative and that's negative, and so it's considered non-polar. So carbon dioxide is a non-polar molecule. Or water is a polar molecule because we can see on both sides they're opposite charge. Here, the charge, it's opposites in the middle, but on the two extreme sides of the molecule, they're the same charge, and so it's considered non-polar at that point in time. We'll talk a little bit more about that when we start doing the structures and that. Okay? All right. The very last topic has to do with this equation right here, And I shared this with you a couple days ago. And it's called Coulombs Law. And it tells you the strength or energy associated with a bond. You don't have to use this in doing any calculation. That's to the minus 19th.
Is it 2.31?
Yep.
Is that joules per nanometer?
Yep. Joules times nanometers. So the Q is the charge, and the R is the distance. Okay, now, I'm not going to do any problems with this. I'm going to see if you guys can figure out how to figure out which one will have a greater bond energy based upon the size of the atom, or the size of the ion. Last chapter we talked about ion size. That if it's, over here, if it becomes a higher negative number and it's in the same period, the atoms get bigger. If we're over here and we get a higher positive charge, the atoms get smaller because there's less electrons and equal number of protons to pull them in. So knowing that trend, for example, if I give you these two atoms, okay, I give you CaF, and I give you CaF2, and then I give you Kf. Which of these two ions, because this is calcium plus 2 and this is potassium plus 1, which of these two ions is smaller, calcium or potassium? Calcium, right? Because it loses 2 electrons versus potassium loses 1. So calcium's smaller. Fluorine's the same one. Okay? Now I'm not looking at charges, just looking at size right now. Okay? So which of these two would have a stronger bond? Calcium or potassium? Because the R is smaller. The distances of the two atoms can get closer together, the nuclei. We can also look at charge. Calcium's a plus 2, fluorine's a minus 1, or potassium's a plus 1 and fluorine's a minus 1. So plus 2, minus 1, that makes this up here bigger. So then you can also weigh that in too sometimes. Is that the charge is bigger for calcium. And so you get a bigger number on top. The R is smaller, which means overall that's the inverse relationship and you get more energy out. So, okay. Assignment is due. We'll give you some time to work on it tomorrow. Okay? Let's have it due on Monday. Okay? It's kind of a lengthy assignment, but you need to work through them. Most of them are odd numbers, so that means you have to, you can look them up, the answers. Okay? So, it's page 405. It's 29 through 37 odd. Okay? Then we're going to add on 41, 43,
Yeah, we can do it.
52, 55, and 56.
This will be Monday, you said?
Monday. 29 through 37 odd. 41, 43, 52. So there's only two that's not where you can look the answers up. I encourage you guys to look your answers up as you do them. Okay?